Hello everyone, welcome to JG Chem Masterclass. Guys, in today's video, we will see the reactivity of lithium aluminum hydride and sodium borohydride, how they differ in their reactivity. We'll see the structures and we'll see the example related to its one of the example. So here again, I'm going to discuss the M.Sc previous year question, and as you know, the reagents are very important, not only for your M.Sc examination, but many questions you can see in your CSIR NET and GATE examination. So we will see the properties. The topic is important for B.Sc student as well because it is very common reducing agent. Students are studying it from 11th 12th, so it is important for 11th 12th students as well. So we'll see one question. With suitable example, explain the difference in the reactivity of lithium aluminum hydride and sodium borohydride. So we know that these are the two metal hydrides. Here you can see the metals lithium, aluminum, sodium and boron. So we know these two are the best reducing agent, and the structures you can see here. Sodium borohydride, you can see the sodium is having the positive charge and the hydride of boron is having a negative charge. Sodium borohydride structure, similarly you can see here lithium and aluminium. Lithium carries a positive charge, more electropositive than aluminium is electronegative, here having a negative charge. As we know that if you go down in the periodic table, the electronegativity of aluminium decreases compared to boron, right? Electronegativity decreases means the hydride bond, the aluminum hydrogen bond becomes more polar, more ionic character. So the strength of this bond becomes weak, means it is easy to transfer the hydride from the aluminium complex rather than the boron, because aluminium hydrogen bond is more polar because of its aluminium's less electronegativity. So more polar means easily it can transfer the hydride, and so it can act best or strong reducing agent, means it can act as a strong base as well as it reduces the carbonyl group frequently compared to sodium borohydride. So basically lithium aluminum hydride is a stronger reducing agent because of this characteristic compared to sodium borohydride. So now we will see some differences which we have already spoke about here. So you can see here boron being a part of the second period, it makes a shorter and stronger bond with the hydrogen. Okay, compared to the aluminium, because it falls in the third period, so it will form the longer and weaker bond. So we know that as you go down in the periodic table, the length of the bond increases, and so the strength of the bond decreases. Okay, so this is the relation which is very common and all the students, they know this relation. As you go down, the strength of the bond decreases and the length increases. Okay, so we can also say that the boron hydrogen bond is more covalent character, and as you go down, the ionic character of the bond increases. Okay, so aluminum hydrogen bond is more ionic, means more polar bond compared to boron hydrogen bond, and because of this the complex, the sodium borohydride complex is less reactive and more polar bond, means the hydride transfer is easy and therefore it is more reactive. And so we can say that sodium borohydride comparatively it's a weak base, and the lithium aluminum hydride, because it can transfer hydride easily and it can act as a, because of the rich electron density, okay, on the complex, okay, hydride ion, it is acting as a strong base. So aluminium is compared to this, you can see more electropositive. Less electronegative means more electropositive. Aluminium is more electropositive, so the electron density around the hydride ion is more, and because of rich electron density, it will act as a strong base. So these are some common differences, as the question is based on the difference in the reactivity. So we can compare the two based on the physical properties. And now we will see how these are effective on the functional groups. So we know that sodium borohydride reduces the aldehyde and ketone group to the corresponding alcohols, and it cannot reduce esters, epoxide, lactones, carboxylic acid, nitro and nitrile group. So it is ineffective against all these groups. So basically, whenever you have aldehyde and ketone group, you can go for sodium borohydride. Okay, and the reaction is performed under alcohol conditions. So either in ethanol or methanol, one can pursue the reaction of sodium borohydride. So in general, if you have aldehyde or ketone, it reduces to, okay, alcohol. So if you have aldehyde, it will form 1 degree alcohol primary, and if you have ketone, it will form this 2 degree or secondary alcohol. While lithium aluminum hydride, you can say here that it being a powerful reducing agent, it reduces almost all kinds of carbonyl functional groups like carboxylic acid, esters, lactones, and hydrides, amides, and nitrile as well. And it reduces carbonyl groups to the alcohol, while amide and nitriles are reduces to amines. So basically, you get less selectivity in case of lithium aluminum hydride because it reduces all these kind of functional groups. And since it is catching if it catches the moisture, so it decomposes. Lithium aluminum hydride decomposes in the presence of moisture and releases a hydrogen gas and convert into lithium hydroxide and aluminum hydroxide. Therefore, to prevent this reaction, the reaction is conducted in the ethereal solvents like THF or ether. Okay, so we should avoid moisture condition, and it is like you should be very careful handle this reagent because of the that lithium aluminum hydride decomposing and it releases a hydrogen gas, and because of that the chances are there to catch the fire also. So we should avoid moisture condition. And so you can have any functional group here, carbonyl, so OH, this is the acid here. You can have OX here, so any ester, or you can have seen just now all the functional groups which reduces first to primarily to aldehyde and later to subsequently it reduces to alcohol. So finally it gives you alcohol. So we'll see a few example here. So let's take one example for the sodium borohydride, and you can see in the molecule you have three functional group: carbonyl, you have alkene, and you have ester also. And we know sodium borohydride reduces the ketone and aldehyde only, so you can do the chemoselective reaction in the presence of sodium borohydride. What is chemoselective? Means in the presence of other functional group, you can selectively reduce only one functional group. So basically in the presence of sodium borohydride, the double bond and the ester group will be untouched, unreactive, and it will reduce only to carbonyl to the alcohol. So selectively you can form and reduce the carbonyl group. So you can see here the same statement is mentioned here. Now we will see the other example in the presence of lithium aluminum hydride. You can notice here again you have two functional group. One is alkene, other is ester group, and we know lithium aluminum hydride is unreactive towards the alkene, but it reduces the ester group to alcohols. Okay, so basically it will form the two alcohol here. So the ester group will be reduced, and subsequent step you can take the water here. In the first step you should not have water. For workup we will take the water here, and you can notice here two alcohols are formed, and one is in the byproduct, and you can remove it after filtration during the workup procedure. So you have here alcohol as well. So the same statements mentioned here. So here one more example, like you can consider, like if you have here carbonyl group and ester group both, it will reduces both. Okay, so and if you have here amide also, that will also reduces. Like if you consider the first example, in the presence of lithium aluminum hydride, the ketone and ester both will reduces to alcohol if you take here lithium aluminum hydride. But if you want selective reduction, you cannot go for lithium aluminum hydride for this reaction. We have to take the sodium borohydride. Okay, so chemoselectivity decreases in the presence of lithium aluminum hydride, while you can do this in the presence of sodium borohydride. So I hope you understood the reactivity of lithium aluminum hydride and sodium borohydride. I will prepare a separate video on the mechanism of sodium borohydride and lithium aluminum hydride. So if you have any doubt in the reactivity, you can write in the comment section. And if you want me to prepare any other reagent or any other video or any topic, you can do write on the comment section. And if you like my video, please do share it and subscribe it, and share it with your friends. See you.